Hi everyone. This is a lecture for Kinesiology 376. This is going to be I think it's going to be the fourth week um, for Kinesiology 376. In this lecture, we're going to talk about angular kinetics and the important parts of it. This will be tested for exam 3. And we're just going to be looking at, the forces that cause angular motion, how we can either manipulate them, calculate them, the important parts of them. A good reason to look at this is if we're looking at somebody trying to perform a triple axel. So we're going to, hopefully we can see this video here, and she is going to perform this triple axel here. And what we're looking at, what she just did there, what we're looking at is we're looking at how she can increase her angular velocity quick enough so that she can perform that triple axel before she lands back down on the ice. So we look at this stuff because we need to, while she's in the air, she needs to build up her angular velocity. To do that, we're looking at the angular forces that she is producing here. And she does this by changing her body position. So let's start talking about angular kinetics. So much like when we looked at our linear and angular kinematics, the angular kinetics are very similar to their linear counterparts. So when we look at linear displacement, we have angular displacement, but instead of saying meters or centimeters or whatever we're using, we use degrees or radians. The same thing for linear velocity when we're talking about meters per second. In angular velocity, we're looking at degrees per second or radians per second. For our acceleration, in our linear kinetics, we have meters per second squared. For angular acceleration, we're looking at degrees per second squared or radians per second squared. And the same thing when we look at force in newtons, but instead we have moment of force. In linear kinetics, we talked about force as it is expressed by newtons. In moment of force, we're looking at Newton meters. Newton meters. Another way of looking at that, another term for moment of force is torque. Okay, Torque. Okay. Then we'll look at, linear inertia and moment of inertia for angular kinetics. We have linear momentum. We also have angular momentum. And we have linear impulse. We have angular impulse. And much of the calculations we do are very similar between linear and angular kinetics. We're really, once again, pretty much just swapping out the units. So let's first talk about our moment of inertia. It is the resistance to change in angular motion. So much like our linear inertia, where it's resistance to change in linear motion, moment of inertia for angular is the resistance to change in angular motion. And it's related to, once again, mass, where we see it with an increase in mass, we see an increase in resistance. That leads to an increase in moment of inertia. So if something has more mass than another object, it's harder to change its angular velocity or its angular motion. Plus, it's also related to the distribution of mass with respect to the axis of rotation. If it has a longer or greater axis of rotation or radius of rotation, it's going to have a higher moment of inertia. And our units, we're using kilograms per meter squared. We also use Newton meters or something like that. But unless I specifically state otherwise, you're using kilograms meters squared. So an example of this, let's say we have two similar baseball bats with the same mass, but the mass is added at different positions. We see A and B here, with A, the mass added to the very distal part of the bat, and then B, it's added to just before the beginning of the handle. So which bat is harder to swing? Well, we need to know which bat has a greater moment of inertia. So much when we looked at linear kinetics is we're looking at not just the masses, but how far they are from, or how large the radius of rotation is, or the axis of rotation. If we look at from here to here, this is, we'll just make up numbers here, but we'll say this is 0.75 meters, and from here to here, we'll just say this is 0.25 meters. These numbers really, I just decided to come up with these numbers. They really don't mean anything. So you can use whatever numbers you want here, but we know that this is greater, A is greater than B. So A is going to be harder to swing. It's going to require a greater moment of force to begin that swing, to overcome that bat's moment of inertia. We'd also say it requires greater torque. Similar to when we were looking at if you're working on a bolt that's very hard to loosen, you may use a longer wrench. It's the same example. So A would be harder to swing. We can also look at this if we're looking at backpacks. Okay, so when you were in, primary school and you had, all your books in your backpack, it would become very heavy. But when we look at that, it's not so much that the backpack is heavy, but also how you wear it. A lot of times you'll see people wearing their backpacks with their straps, and so the backpack almost hangs over their butt and it hangs really low. That's increasing that axis of rotation. If instead you wear your backpack higher, so it's over your butt, or it's superior to your butt, if we're using biomechanics, it will make it easier to carry. I hope that makes sense. So for the human body, it's impractical to measure each part of a body's mass from the axis of rotation. It becomes kind of messy when we're doing that. Therefore, we express these values as the radius of gyration. Okay? This is noted as K in our math, but it is the distance from the axis of rotation to the point at which the mass of the body can theoretically be concentrated. This point is not the same as the center of mass. In fact, very, very long ago, when we were trying to quantify K for each body part, a lot of times what we used were cadavers. So we'd use a cadaver's arm, a cadaver's leg, we'd use, the lower leg of a cadaver, and they would put this on essentially a gyrus so they could spin it, and they figure out at what point does the rotation of this leg look so it makes a more perfect circle, and that was determined to be the radius of gyration. Okay, so once again, the radius of gyration is the distance from the axis of rotation to a point at which the body, to the point at which the mass of the body can theoretically be concentrated without altering the inertial characteristics of the rotating body. So once again, when it's rotating, it's not rotating and causing a lot of vibration or anything like that. It's spinning more balanced, if that makes sense. So we have two components when we're trying to calculate the moment of inertia. We have the mass of the object and its radius of gyration. So which one's more important? While this is a multiplication equation, more or less, they both contribute to the value of moment of inertia. But the radius of gyration may be more important because when we're looking at the human body, well, we can't really change the mass of the object or the body part, at least not readily. So when we're looking at this, we can modify the radius of gyration. When we were looking at the ice skater performing a triple axel, she modified her radius of gyration by tucking in her arms closer to her body. So you can look at this too, and we'll look at that when we start talking about angular momentum, or the conservation of angular momentum, is that when we find that if we are spinning or rotating at a certain velocity, if we abruptly decrease the radius of gyration, or we could call it the moment arm or lever arm, angular velocity will increase. And then if we lengthen the radius of gyration or increase the radius of gyration, moment arm, lever arm, whichever you want to use, we'll be using radius of gyration here, you will slow or decrease the amount of angular velocity. You can try this with yourself too. If you are sitting in an office chair that spins, you can start spinning in your office chair and then throw out your arms and legs, and you should notice you're slowing down. But if you then tuck your legs and arms back in closer to your body, you'll start speeding up a bit. So why? So we can look at that as far as choking up on a bat. What does that do? Okay. It decreases the moment of inertia. So once again, if you're looking at a batsman in baseball, or a batter, excuse me, you may see that they're swinging really hard, but they can't contact the ball. Either they're missing it, they're swinging too soon, swinging too late. They really don't have control over that bat. Now you could say, well, they can use a lighter bat, but if we're looking at, college or professional, usually there's only really one weight for that bat, so you can't really change the weight of that bat. But you could tell them to choke up on that bat, because by decreasing that moment of inertia, you're making it easier to swing. So it's going to increase their control. However, if they choke up on the bat, they'd have to swing it even faster to hit the ball further. Okay, so it does decrease the linear velocity of the ball if the ball is struck. So during walking, we have a relatively low angular acceleration of our lower limb. So how much, and this is determined by how much knee flexion we do how much knee flexion we have during walking. This is a very kind of cool concept when we look at human gait. When you're in your kind of mid to terminal swing phase of your gait, we see that your leg is flexed at your knee. This decreases that moment of inertia of your leg so that when you're trying to swing it, it's much easier to swing. And then at kind of in the middle of that terminal swing, your leg goes into extension. So now you're increasing the angular momentum of your leg. So it's not really, you're not really using free energy or anything like that, because we know you can't create or destroy energy, but it becomes much, much more efficient. You're using that energy better. Okay? So what influence does the knee flexion have on inertia of the lower limb? It's going to decrease the moment of inertia. And so that makes it so we can do kind of the forward part of our swing, we can use that much more efficiently. I hope that makes sense. So during walking, how much knee flexion do we have during walking? We have relatively small amounts, but it leads to a significant amount of efficiency. Okay? So when we decrease the radius of gyration for the shank, which is our lower leg and foot, we are decreasing the moment of inertia. So when we do that forward swing of our leg, we use much less energy to do that. And the moment of inertia is typically determined in each of the three principal planes, okay? The frontal, sagittal, and transverse planes. The principal moment of inertia, what we call it, is the total body movement of inertia relative to one of our principal axes. So we have the rotation in the frontal plane, or rotation about the frontal axis, and we'll say that's 10 kilograms meters per squared on average. In our sagittal plane, rotation in the sagittal plane, or rotation about the transverse axis, we'll have 10 kilogram meters there. We might have 2.5 kilograms meters if we tuck up our arms and legs. But if we then extend both of them, we increase, once again, that moment of inertia. So when we're looking at Olympic divers, they will start their kind of bounce on the springboard in this sort of position, at the normal kind of relaxed position. When they're up in the air, what they do is they kind of tuck in, so that's decreasing their moment of inertia, so they can increase their angular velocity, so they can do multiple tumbles while they're still in the air. However, before they start going into the water, they'll lengthen themselves out so that they can slow down, so they can make sure that their arms and head enter the water first, so there's very little splash. And there's a nice little video right here that kind of demonstrates that. When we're looking at our transverse plane, okay, or rotation about our longitudinal axis, this is our, you spinning in an office chair, or that ice skater doing a triple axel, okay? When we're kind of in our normal position, we might have a moment of inertia of 1 kilogram meters squared. But if we were to extend our arms outward, or abduct our arms, sorry, not extension, but abduction. So this is our abduction. Okay, we are going to increase that moment of inertia in our transverse plane. So once again, if we wanted to decrease that, they may adduct their arms so that they're closer together. So it's going to decrease that moment of inertia, so then increase our angular velocity. Therefore, changing the body configuration alters the moment of inertia. This is important for skills like diving, figure skating, and it relates to angular momentum. So let's talk about that again. There's another kind of good example is we're looking at torque. Okay, torque is a turning force, or what we consider to be moment of force. This is the angular kinetic analog to our linear kinetics of force. So anytime a force acts through a place other than the center of turning, it will produce force. So we can look at this in another example besides sports as cow tipping. Okay, if after the semester ends and everybody can start hanging out again together, you may be at a party where some people have had maybe one too many drinks, and they said, well, let's go cow tipping or something like that. But once again, we're looking at force is important, but the moment arm, or that lever arm, is much more important, or sometimes you hear torque arm, okay? That's more important because once again, that's squared. So when we look at a cow, it has a very long arm here, okay? So it's much harder to tip. In fact, when you look at this, when somebody asks you to go do this, say no, because it's actually impossible to tip over a cow when it's standing, or at least for a human. Their center of gravity is very low, and they have a very large lever arm. They're essentially the Ferrari of the farm. So just say no, thank you. You can talk about them. You can talk about angular momentum and the amount of torque, and you can really impress them, and then hopefully you can save them from doing something really stupid as well. So now let's talk about angular momentum. With linear momentum, it's the amount of motion an object possesses, which is, linear momentum is mass times velocity. But with angular momentum, we're looking at the amount of angular motion an object possesses. And our units are kilogram meters squared per second. Okay? So since this is we're looking at our angular momentum, we're looking at very closely to our moment of inertia. So if h equals I omega, and since I is equal to mass times the radius of gyration squared, then h, or our angular momentum, is mass times, and remember your orders of operation. So first you have to square the angular, or the radius of gyration, then multiply it by the mass, and then you multiply it by the angular velocity, where angular velocity is in radians per second. Okay, so remember this, is if you remember that you may need to convert degrees per second to radians per second, if you're looking at an angular velocity problem. So there are three factors which affect angular momentum: the mass, radius of gyration, and angular velocity. So which one affects angular momentum the most? The radius of gyration again, because it's squared, and also we can't really change, at least not readily, the mass of an object either, okay? So when we're looking at this in a practical manner, is we look at the radius of gyration having a greater effect on the amount of angular momentum. So for example, we can look at a diver. A diver must attain a sufficient linear momentum during takeoff from a platform to reach the necessary height so they can do their somersaults or tumbles, okay? In addition, they must have sufficient angular momentum to perform those rotations. So once again, they may start out very upright, and they use this so they can develop enough power on the springboard to get up at that height. But as soon as they're at that height, they may tuck in, because by tucking in, they're reducing that radius of gyration, so they're able to build up more angular momentum so they can perform all those rotations. And then they'll slow down that before they impact the water by extending outwards so they can enter the water with their hands and feet hitting the water first so that there's little splash. So now let's talk about the conservation of angular momentum. Recall that we do have a conservation of linear momentum. So of course, we're going to have a conservation of angular momentum. In the absence of external forces, the total momentum of a given system, okay, remains constant. This is linear momentum. For when we look at the conservation of angular momentum, in the absence of external moments of force, the total angular momentum of a given system once again remains constant. So remember that moment of force is equal to moment, okay? So let's think for a moment about how you'd accomplish a somersault on the ground, okay? First, you need a backward force is applied to the ground by the feet, which causes the body to rotate, okay? So how does a diver accomplish a somersault in the air? Because they don't have that reaction force that's applied to the ground. They're up in the air, okay? If he or she doesn't have anything to push against, how are they performing a somersault in midair? We're looking at that conservation of angular momentum again, which is our moment of inertia, or a change in moment of inertia to a change in angular velocity. So let's remember, angular momentum is conserved. That basically means angular momentum remains constant. So when we're looking at this figure here, we see that the angular momentum for each of these positions, 1, 2, and 3, is conserved. But if we're decreasing this moment of inertia from 10 to 2.5, from 10 to 2.5 to 12, because angular momentum has a velocity component, is that going to increase or decrease our velocity or our angular velocity? Generally, when we see our moment of inertia decrease, we're going to see our angular velocity increase. So let's take a look at the maths here. So let's look at the maths for these three positions. And we can rework our angular momentum. This is our angular momentum equation right here, to determine the angular velocity of this person. Okay, we're simply dividing by omega on both sides here, so we're left with omega being on the left side. Okay, so now we have omega, or our angular velocity, is equal to the angular momentum divided by the moment of inertia. So if our first position, we have our moment of inertia is equal to 10 kilogram meters squared, okay, and we divide that by 10 by 50, okay, we'll say that they had an angular momentum of 50, they are going to be rotating at 5 radians per second. If, however, we decrease in position 2 here, okay, if we decrease that by 2.5 kilograms meters per second, we're decreasing that moment of inertia by kind of tucking in, we increase our angular velocity to 20 rads per second. And then finally, in the finish here, as they're about to enter the water, they lengthen out or extend outwards again. So they're increasing that moment of inertia. So we're going to see our angular velocity decrease again. Okay, it's going to decrease to about 4.17 radians per second. Okay, so once again, this could be, you're spinning in your office chair. If you're spinning with your kind of legs and arms kind of outwards, you're going to be spinning slower. But then if you tuck your arms and legs towards your body, it's going to start feeling like you're spinning quicker. Okay, you increase your angular velocity by decreasing your moment of inertia. And you can decrease or increase your moment of inertia the best by altering that radius of gyration. Remember K, okay? This is the most important part because we look at K is squared, and it's easier to kind of reduce that radius of gyration than, all of a sudden somehow changing your mass. Okay, I hope this is making sense. So we do this a lot when we're looking at tripping. We do this in our veer lab. Okay, so the moment of inertia is very important here. So this person is walking on this treadmill, and their moment of inertia just changed there. Okay, that can lead to falling from a trip. Okay, so once again, let's look at the conservation of angular momentum. In the absence of external moments of force, our external moments of force, remember, a moment of force is equal to just force if we're looking at linear kinetics. In linear kinetics, we just say force. In angular kinetics, we say moments of force. So in the absence of external moments of force, the total angular momentum of a given system remains constant. This sure looks like a good exam question. Just saying. So, once again, let's take a look at rotation. Remember, when we rotate clockwise, that's going to be negative. When we rotate counterclockwise, that's going to be positive when we're looking at our displacements. So right here, this girl is rotating clockwise. So which way is the trunk rotating? Clockwise. How are the arms moved to compensate, though, so that she does not fall? They're going to move in the equal and opposite direction. So they're going to move counterclockwise. Okay? This way, she's remaining balanced. She's keeping her center of mass above her base of support. So due to the conservation of angular momentum, when a person rotates body segments while airborne, there is a compensatory rotation of other segments, and this produces an equal amount of angular momentum in the opposite direction. Remember Newton's third law of motion, equal and opposite? This holds true in angular kinetics as well. So in this way, the total angular momentum remains constant. Therefore, to move the body in a clockwise direction, we rotate our arms in a counterclockwise direction. So once again, we'll look at another example. A person is tightrope walking with a pole. She starts to fall in one direction. We'll say she starts to fall to her right. In what direction should she tip the pole to correct her balance? Should it be, if she's falling towards the right, should she tip her pole to the right or to the left? She should tip it to the left. If she were to tip it to the right, she's going to fall over very quickly. So she should tip it to the opposite direction. We can also look, there's also a good example here as well of affecting that radius of gyration. Remember K again, okay? So if you were to look at someone that's learning to tightrope walk, okay, some people, when they get very good, they don't use a balance pole at all because they can control their body very well. But when they're starting out, they may use longer poles, okay? When they use a longer pole, they're increasing that radius of gyration so that they can maintain their body upright just a little bit better. So once again, we're still looking at this right here. Our radius of gyration is still one of the very, very most important factors in angular kinetics. Let's finish up and we'll talk about angular impulse. With linear impulse, impulse is equal to area under that force times curve, basically force over time. But with angular impulse, we're looking at the area under the curve of the moment, or area under the moment of force time curve. So these are very similar, okay? But once again, we're just looking at kind of different units. So angular impulse is moment of force multiplied by time, okay? And our units are Newton meters seconds, okay? Not Newton meters per second, Newton meter seconds. This is multiplication. So finally, this is the take-home message. Similar to linear relationships, the angular momentum can be increased by either increasing the magnitude of the movement or the increasing of the duration, okay, that is applied, or a combination of both. This is similar to impulse in a linear fashion. Remember, we had those two graphs, okay, where we're looking at time and force, okay, and we saw that we can either increase force or we can increase time like that, okay. We can do the same when we're looking at angular momentum as well. So this right here, once again, may be a really good exam question. So that's it for this lecture. This lecture is a little bit quicker, similar to, when we were looking at kinematics, is if you've got a good handle on the linear component of kinetics, really the angular component is not much different. It's very much the same as kinematics. We're just looking at it, instead of looking at motion in a straight line, we're looking at it as it rotates about an axis. So I hope this made sense. I hope these lectures are helping. If you still have questions, feel free to contact me through email. We can set up an individual Zoom meeting. I've already spoken with a couple of you. I hope that helped, and I've helped a little bit with some of your homework questions as well. And we also have office hours every Friday from 8 to 10 a.m. So I hope to see you there. Goodbye.